through Hubble's telescope.
I can get rid of this. Okay, thank you very much, Pithapuram Degree College, for inviting me to give this talk. Okay, so let me take you through a journey of photographs and the physics behind it, the technology behind it. So I'd like to thank my previous speakers because some part of that of my talk, which were essential, were covered by them. So, no, the Hubble Space Telescope is known as the granddaddy of space telescopes. Why granddaddy? I will come to it later. So Hubble is the first NASA great observatory. So there are 4 telescopes in this great observatory. So Hubble Space Telescope is actually a low orbit, that's around 559 kilometers above the Earth, and it is going around the Earth every 97 minutes. Okay. The next question is, how big is Hubble? So just to get a dimension of it. So it weighs around 12,000 kgs on Earth. So in volume size, if you look, it would be like a school bus. So what is the equipment that is on board? So obviously the primary mirrors, the secondary mirrors are there. Then there are main cameras, light splitting devices, which are known as spectrographs, gyroscopes to keep it oriented in space. Sorry. It was launched in 1990 with a life expectancy of 20 years. Now it's almost 30 years, but it is still working. Thanks to the maintenance work which was done on the Hubble Space Telescope. Now, you would say, why Hubble Space Telescopes? Okay, and what is its contribution? So the following are the contributions, if you can look at it. The formation of star factories, we could see the formation of the sun and the solar system. The age-old question has been answered, right? The violence of exploding stars, so new light on black holes, the age and size of the universe. Hubble revealed where dark matter exists, and it also has provided evidence for an unseen force called dark energy. Okay, so these are its contributions. So I would like to take you through a journey of, or plan of my talk would be Hubble and equipment on board, astronomical images and the need for coloring techniques. I think previously Sir was talking on physics of colors. So I can go fast there. Images of star factories and how to read the images using different coloring techniques. So we see a lot of beautiful pictures on the internet. Okay, so what they actually mean. So that's what I would like to look at it. Why study spectral lines, formation of planetary systems, death of stars, black holes, Hubble's deep and ultra deep field views, some light on dark matter and dark energy. So these are the contributions. So this is normally a course which I give for 4 hours. I had to curtail it down to around an hour or so. Okay. So why the granddaddy? It is because it was one of the first telescopes to be launched by NASA. After that, they launched Compton. Hubble basically looks in the visible range of the spectrum, UV and near infrared. Okay, and then they had launched Compton, which looks into the gamma ray space, and Chandra, named after Chandrasekhar, it looks into the X-ray spectrum, and Spitzer, which looks into the infrared spectrum. There are other telescopes which were launched by different agencies, that European Space Agency, Planck's Observatory to look at the cosmic wave microwave background. India also has a telescope AstroSat, which was launched in 2015, a life expectancy of 5 years, so it's still operational. So these are the 4 telescopes which were launched by NASA. So this is here Hubble, which is on the visible. I have put those pictures on these spectrum. So infrared, you can see Spitzer, it shall be here on the spectrum. This area of the spectrum will be covered by Hubble Space Telescope. The X-rays will be covered by Chandra, and the gamma rays will be covered by Compton. Now, how does Hubble communicate with the space center down to us, and how does it send the data? Okay, so basically Hubble is pointing towards some light. It collects light. The raw data is sent to a tracking system. The tracking system sends it to the ground station, and the ground station transmits it to the Space Telescope Science Institute. And after that, the data is released. Okay, just to give you an idea of the spectrum and the size of it. And so if you look at radio wave frequencies, it would be around few 100 meters. This is in centimeters. To the other end of it would be 10 raised to minus 12. So you have nanometers, angstroms, and so on. So as you go away from radio wave to gamma rays, so the NASA space telescopes, all 4 telescopes cover different areas. So Hubble basically is going to cover this area, a bit of ultraviolet and a bit of infrared. Now, this would be what a Hubble, it's not a complete picture, but just to give you an idea of how it looks like. It has solar panels which power the supply, right? So this is the aperture. So it has nickel hydrogen batteries, which are I think now replaced with lithium ion batteries. So you have the primary here, mirror mounted here, the antennas, the gyroscopes, and all the other equipment of spectrographs is kept here. So you have the wide field camera here, so the advanced cameras, and so on and so forth. So these are the cameras which are fit into the Hubble Space Telescopes, and this is the part of the spectrum which they cover. Okay, so this is what they would look like, and this is the part of the spectrum. So let us look at in detail one by one. The first one, as I said, it is advanced camera survey. It has 3 cameras on board, and it covers right from 1200 angstrom, that is ultraviolet, to infrared. Then we have wide field camera 3. It covers visible, near ultraviolet, and infrared. And the resolution of this is much greater than the other instruments here because it was replaced. And then we have COS, that is cosmic origin spectrograph, which basically looks into the UV region only. But it is a very sensitive instrument. The sensitivity of it is around 10 to 70 times. So basically, if you're looking at very faint objects, then the sensitivity becomes very important. And this is, you use this camera. The other is an NICMOS, which is near infrared camera and multi-object spectrograph. Okay, so as the name suggests, it is looking at near infrared. And the other is STIS, that is Space Telescope Image Spectrograph, used to obtain. So this is looking at images which are already resolved, but with a better resolution. That's what we want. What is the other things which are there is BAPS, that is berthing and positioning system. So you have to maneuver it, you have to point it in space. Okay, the other terms which you would see is GSFS, that is the center where the space telescope is controlled, and the other is a fine guidance system, which keeps it oriented in space. Now coming to, when we are talking of telescopes, we have to talk of the resolving power. Now, just to give you an idea of how the resolving power goes, if you take a human eye, the resolving power is around 60 arc seconds. Now, what is an arc second is, you know, a circle is 360 degrees. So 1 degree, if you divide it further into, that will give you 60 minutes. And then 1 minute will be further divided into 60 seconds. So we are talking of the resolution of a human eye, which would be 60 arc seconds. The human eye diameter is around, you can take it as 4 mm. Galileo's telescopes, the diameter was maybe around 8 mm, yeah, 8 to 10 centimeters, I think. So the resolution there is 3 arc seconds. Then you have the Earth-based telescopes, which have a resolution of 1 arc second, and Hubble has a resolution of 0.05 seconds. Okay. No physics is complete without few equations, so I had to put at least one equation. Yeah. So basically, you can, I'm not going to details of this. This is the formula for this, and then this is how you calculate it. Okay. So I think everybody does this formula for resolving power of telescopes and microscopes and so on and so forth. So let's look at a schematic of how the Hubble is there from the, so this is where the light enters. The light, so it's a reflecting telescope. So the light falls on this primary mirror, which is all focused to a secondary mirror. And then after this is focused on the secondary mirror, it is sent through this to the equipment, and where it would be analyzed. Okay, so this is something which would act like a magnet, and it would orient towards the Earth magnetic field. So there's a few of them. Okay. Ilagar, I'm audible, no problem with it?
Yeah, yeah, you are very much audible.
No, sometimes I have to. So the primary mirror, so the diameter of this primary mirror is around 2.4 meters. So it is the one which is going to capture all the light. Now you would say, why put a telescope in space? The main reason for that is that we don't want the Earth's atmosphere to pollute the light which is coming into the atmosphere. So you put a telescope which is in the orbit. So, but this is a low orbit telescope. We need to understand that it's not at a very high orbit. So when it was launched in 1990, and the first images which they got were blurry. Now you have spent crores of rupees, and then the images which are coming out were blurry. So they searched for an answer, and they found that it was due to spherical aberration. Now all physics students know what spherical aberration is. Okay, spherical aberration is that means the mirror somewhere is not polished properly. Now these are all parabolic mirrors, not spherical mirrors. You should understand that. If it's a spherical mirror, it will not focus to a point. And you know, you learned in a parabola, there's only a single focal point. So all of them are in parabolic shape. Now let us look at what was the aberration. The flaw in the polish of the mirror was 1/50th of the thickness of a sheet of paper. So you can imagine it is 1/50th of a sheet of paper, means that is the difference in the thickness at a few places which was there, and this was giving blurry images. Now what do you do if your vision becomes blurry? You use glasses, right? So but now how do you correct this, because the telescope is already in space. Okay, so they had to send space missions to repair Hubble, and that's where they did it in 1993. A series of small mirrors was used to intercept this light which was flawed and correct it. Okay, so and astronomers also replaced the few of the equipment on board, and they replaced the wide field planetary camera with wide field planetary camera 2. Okay, so I'll skip this. So the coaster is nothing but that small mirrors which will fix this. So these are the astronauts who are actually fixing the Hubble Space Telescope. It is docked to the station, the space shuttle, and then the repairs are carried out, and then Hubble is left back. Normally when they leave it again back at a slightly higher altitude, so that because Hubble is deorbiting because of the atmosphere. So these are the space missions where 5 space missions were carried out, and after that the space shuttle was dismantled because after Challenger was burnt out when it entered the atmosphere. So mirror images shown here mostly contained images from wide field planetary camera 2 and wide field camera 3. Okay, so wide field camera 3 was the last one sorry, to be installed. Wide field planetary camera had 48 filters. Now there were some narrow band filters and broadband filters. Narrow band filters normally used for studying atomic transitions, and the broadband filters were used for studying colors of stars and galaxies. So if you want to study galaxies and stars, you will have to use the broadband filters. Let us look at the history of how this images started. So you all know that Galileo was the first one to use the telescope to look at the foliage. But when he published his papers, he didn't have any images. So what he had done was he drew those images with hand and then published his paper. In the beginning 20th century, people started using filter cameras. So they used to have red filter, green and blue, and each layer they used to put one on another and then finally produce an image. So astronomical data from modern telescopes are no longer captured on films. As sir has already pointed out, you use CCDs. They are digital that require processing in order to create an image. Sorry. So the journey is from hand-drawn images to photomechanically produced images. The idea was that we want to eliminate the human hand in it. So let's look whether we are able to do that. So complete objectivity and neutrality in the interpretation of scientific data in pictorial form is not feasible, nor is it desired. So basically you have to translate this ones into zeros into pixels. The data received by the telescope has a variation of brightness with no inherent color. The CCD is not going to, in our case, is not going to capture any color. So the pixels are not like RGB pixels. They are all pixels which are going to have a monochromatic images they're going to. So, but how do you create those color images? So that part of the data will come from the filters. So astronomers can see from radio frequency to gamma rays. So all of you know that we can see only visible part of the spectrum. So I will have to add color to these images even in ultraviolet and infrared. So image processors put together the color map that translates a portion of the data into various colors. So Hubble is using CCD, so I think I'll not go into those because sir has already covered. So CCD cameras, see the ordinary cameras which you have, they have pixels which are red, blue and green put side by side. Okay, So, but in Hubble, it's not like that, because you want to make use of the maximum space available there. But the telescope does have various filters. So that's where the we know the filter we are using, and we know the light. The photo of the same object is taken through multiple filters. So if you're looking at an object, so you change your filters and take the images. Scientists can then combine the images and assign colors to those images. Now, for faint objects, you'll have to wait a bit longer, because there will be only few photons coming in. Maybe in a day, only 10 photons also can come in. So you have to wait. Okay. So now you would say, which is better, taking monochromatic images or the RGB images? Now there is upside and downside to both of them. Using color camera saves times. You click, you would not like to wait to take a photograph, right, on Earth. So, or your mobile cameras or the other cameras. So that's fine. But here in Hubble Space Telescope, we are going to use a monochromatic camera. So what we want is that any photon which strikes anywhere on the space should be recorded. The camera gives you more freedom of which wavelength you're looking at the image. Okay. And since you're using filter, you will be catching less light, because the other photons have been cut off, and therefore you need a longer exposure. Which method is better depends on what you are going to image, the type of image you want, and the time you're able to willing to spend on this single image. Okay, so this is the criteria. Next, you would say, why add color at all? Okay, if the color involves manipulation, wouldn't it be better with the original black and white versions? See, why do we need to do that? The assumption is that behind manipulations, see, you're spending crores of rupees of government money. So finally, you have to tell the general public also what it is being spent on. Okay, to add value and information. So when you comes in the public domain, people appreciate that. So you're adding a value to the information which you are generating. Make the presence of the data aesthetically pleasing. Make information accessible through those photographs. Make material understandable. So I'll come to that a bit later. Color is used as an analytical tool here. Okay. So a human eye, sorry, or a Earth-based telescope will not be able to see a very, very faint object. But I would like to put it on the photograph that there is an object which is faint, but it is there. So I need to add some colors to that. Color is used to depict infrared and ultraviolet. Color can highlight delicate features that would be otherwise lost in a photograph. Okay, I should know what am I looking at, what is the information coming out of it. The term false color is often used to describe astronomy images, whose colors represents outside the visible portion of the electromagnetic spectrum. So the RGB colors are chosen to represent characteristics of what? I can color the whole image through just having temperature as a criteria, or energy, or chemical composition. So when you look at a Hubble image, you should look carefully that what is the color combination of that image and what those colors are actually indicating, whether it's temperature, whether it's energy, or whether it's a chemical composition that you're looking at. False color images are only a matter of different visual codes. Okay. Now let me come to this Eagle Nebula, which is the most celebrated image of Hubble. It was one of the first images. Now you have two images side by side here, the image 1 and 2. Okay, this is also known as pillars of creation. This image is taken by an Earth-based telescope. This is taken by the Hubble Space Telescope. Now look at the color code. So 673 nanometers is assigned red. Okay. So all of you know that red is around 6,000 and violet is around 4,000. Okay. So when we looked at the spectrum, 657 nanometers, which is again red actually. Okay. Is assigned green. And 502 nanometers, which is around turquoise blue, you can say, is assigned blue color. So you are not assigned the actual colors here. Now look at the Earth-based telescope. 650 nanometers is red, you have assigned red. 539 nanometers green, you have assigned green. And 451 nanometers is blue, you have assigned blue. So a human eye would see this. But the Hubble Space Telescope is using a different color combination. So it is not a one-to-one correspondence. So here 657 nanometers, which is red, but in the photograph, it is going to go as green. Okay. So look at the difference in this. Yeah, what they actually mean also will go to that. Okay. So this is what would look like. But then this photograph is much more, has much more information than this, even though it is the actual color which you have assigned it. So both images are actually composite images from 3 monochromatic images, right? So filter use 673, I have already explained, is red. Okay, but I have assigned it red, but here this is red, but I have assigned it green. Here it is green, we have assigned it blue. Here it is red to red, green to green, blue to blue. But how many, okay, so this is what we would actually see. But why has Hubble done this? So some people would say the color in the Hubble images are fake. Okay, it's not a one-to-one correspondence. The other image was an actual image, actual color, because the images don't reflect what it would look like to the human eye. But most color images are fake if you take it like that. Okay, why this has been done? Because this image is not representing the temperature, you can say. This is representing the chemical composition of the images which are there in that pillars of creation. So actually 673 nanometers is ionized sulfur. I mean, if you take ionized sulfur in the laboratories, you will get 673 nanometers. That has been assigned red. So it is giving red, we have assigned it red. Okay. So ionized nitrogen and hydrogen alpha, part of the spectrum is red. This also is red in the spectrum, but we have assigned it green. And 502 nanometers, that is oxygen, it is again ionized oxygen, which is green turquoise, we have assigned it blue. So basically, I mean, I'm looking at this image, you have to look at a more of a chemical composition which is there, the elements which are giving the spectrum. So this different views can help to better see and understand the structure of this object. So what is the color code used by Hubble, or they also known as Hubble colors? So sulfur is red, hydrogen is green, oxygen blue. So when you look at this image, okay, so wherever you see blue, you have to think there is oxygen, right? When it's greenish, you'll have to take as a hydrogen, and wherever you see reddish, it is sulfur. So this is how you read the image. Okay. So therefore, should we say that the image as fake? The images are not fake. For example, if you photograph yourself in an infrared region, okay, so you would look different in that image. But as a person, you're not a fake person. So it is an image of you only, but in a different bandwidth. Okay. Now this is, you can see the picture on the left hand side. This is what actually Hubble sends. So it's a black and white photograph, right? So, and then you add colors to this, you would see that this image is not a square. There is like no the step sort of thing, because this image was taken with 4 cameras, and when you want to finally create an image, all the cameras have to be brought to the same what do you call uh, resolution. Okay, so the cameras are at different resolution, so you have to scale down the images to the same resolution. It's nothing that no, this is small, therefore it is a cut or something. Nothing sort of like this. This image was taken by 4 cameras and they had to be combined with the same resolution. So therefore you would see that. So here you can see that this image is taken by Wide Field Planetary Camera 2. Okay. And this image itself is 5 light years tall. Huh? So we need to look at this. This is not just a small image. So if light starts from here, it will take 5 light years to reach there. Now this is the same image of the M16 or the Eagle Nebula, but this image has been taken by Wide Field Camera 3, the next version of it. So here oxygen is blue, sulfur is orange, and hydrogen is green. Now you can see here there's a lot of halo, which is bluish greenish. So that means there is a lot of star activity going on. This is the nebula, and the stars are getting formed there, and therefore there's a very hot place, and therefore the gas around it would get heated up, and that's why you see an halo sort of thing. You can see it here, you can see it here, you can see it here. So this is in the visible range. Now I'll show you the same image in infrared, how it looks like, and the same image in X-ray region, the same picture. Okay, so the same picture which is taken in an infrared region. Now you can see that most of this dust you can't see in the infrared region, you can see inside. And you can see that there are a lot of stars beyond as well as within the pillars of creation. But here you see it is still dense and you can see the halo, right? So this is where the stars are being born. Let us look at the same image from X-ray point of view. So this was taken by Chandra. Okay, now you can see this blue image here. Okay, so most of the stars when they're being born are very active. They are emitting a lot of X-rays. Okay, and so we can actually see that yes, this halo is there. So we can pinpoint out that there is a star which is being born, and the size of it is around 4 to 5 times that of the sun. Okay, so am I clear? So I have shown you the images of pillars of creation taken from different cameras, how they look like, okay, and so on. So the Hubble's colors is red for sulfur, green hydrogen, blue oxygen. So this are the same images. Okay, image 1, which is colored wherever you find this traces of sulfur, you color it red. Then you take the image wherever you find hydrogen, you color it green. You take the image wherever you find oxygen, you color it blue, and then combine it. So it would give this size kind of a image which is there. So this image has been produced from 48 images, 48 pictures, sorry, not images, 48 pictures sent by Hubble from infrared to ultraviolet. Now this is another picture of the Lagoon Nebula. Now this picture in the top is an actual picture taken with a color camera on the Earth. Okay. Now to this picture, I want to add what are the elements which I have found through the Hubble Space Telescopes. So on that picture, we'll add wherever we find traces of hydrogen, oxygen, and sulfur, we will use HOS, hydrogen, oxygen, sulfur. So if it is reversed, then you need to see how it is done. Okay, so here it would be red. Yeah, this is green, blue, and red. Eli garu, is there?
Yeah, please go ahead,
Yeah,
sir.
yeah.
10 more minutes, we have time.
I'll try to.
Maybe that is not sufficient for you, I think.
Yeah, I'll try my best. I'm
Yeah,
already going fast.
yeah,
Yeah.
yeah.
So now this is an image. Uh, Now here, the chemical elements information is not there. If I look at this image, I have to look at the spectrum. So any energy between 2 and 3.3 kilo electron volt will be coded as red. 3.3 to 4.7 will be coded as green, and 4.7 to 8.8 kilo electron volt will be coded as blue. So here, and this image is not taken by Hubble, this is in the X-ray region. So now the other important part of any astronomy is that spectroscopy. So I think all physics students do some spectroscopy in the lab. So take it seriously, because it's one of the fundamental tools which scientists use to study the universe. Why to study it? Because the spectral lines will give you information about the elements, temperature, density, magnetic field, speed at which the stars are moving, the angular speed, mass, size, and the material around the stars. All this information can be got from this. Now the other is what is the chemical composition of the stars? Now the chemical composition of stars, now as I said, does that mean that the chemical composition of stars varies widely? Initially, our scientists thought the answer was yes, but then you actually use the Meghna formula, and then people were able to show that no, it is 90% is hydrogen and 10% is helium. Okay, and then there's the interstellar medium, which I'll skip. Now let's come to the star formation, how the stars are formed. So if you look at the tips, these are all the points where you can see some activities going on. These are called as eggs, or also evaporating gas globules. Okay, this is the first stage of star formation. After that, as the core temperature increases, because it is accumulating a lot of dust and this thing. So this is an image where you can see this 4 stars. Now this is taken in the visible range of Wide Field Planetary Camera 2, and this is taken in the near infrared camera multi object spectrograph. Okay, now you can see that this 4 points, they look very, very bright here in the infrared. So there's a lot of activity, so that means they are still getting formed. So it's the same picture, but taken in different, with different cameras and different part of the spectrum. I'll just complete this formation of solar systems in one slide. Normally you would say, how was the Earth formed also? So it's basically a protostar which starts forming, and then the core lights up, and when it lights up, it is going to throw all the material surrounding it. So it's going to push all that material outside, and those materials over a period of time will come together, form lumps, and okay, and maybe form some planets and so on. So you can look how many years it takes for this. So people are looking for solar system or like us elsewhere. So the stars have been formed. So will they die? Yes, obviously. Something which is born will going to be dying. So eventually the stars will deplete their fuel. They're going to burn their fuel, and then they're going to die. How are they going to die will depends upon how they are born. Okay, so if you take like a sun, then the sun is going to become a white dwarf, a red giant and a white dwarf. Okay, so if they are much bigger than more than 8 times the size of the sun, okay, then they will become a red giant and a neutron star. I'll go to that slide. So this is, you can say, life cycle of a star, just like you say study life cycle of a butterfly or something, right? So these are the nebulas, right? Then they start accumulating all the dust clouds, okay, and then the core starts heating up, the air forming the eggs or the global globules, okay. Then you have a protostar, okay. Now, if it is smaller than the sun, it may just go to a brown dwarf, okay. But like our sun, once a protostar, the star is born, it goes on the main sequence, what is called as the main sequence. So now the sun, our sun, which is the nearest star to us, is on this main sequence. And someday it will become a red giant, okay. So when it becomes a red giant, the whole earth and everything will be wiped out. Then it will become a white dwarf because it will be still radiating some energy which is left out. And then finally that emission also will stop and it will become a black hole. Now I said, depending on the mass, if the mass is more than the 8 times, then that goes into what is called as a supernovas. Now, and if it is more than 30 times, it will be, the supernovas can go as a black hole or a neutron star. So when they die as a neutron star, okay, or when they die as a white dwarf, this is where they're going to throw the elements from the core, some of it. And then this dust comes back again to the nebulas, and then this goes on. So this is a red giant to a white dwarf. Now here you can see that this is taken by Hubble Space Telescope in the Helix Nebula 2004. Here you can see oxygen. So wherever you see blue, that is oxygen and hydrogen, and where nitrogen is red. Okay, so this is how it looks like. So supernovas, I told you, supernovas will basically emit in X-ray, okay, visible as well as infrared. So you have to use all the 3 data. Now you would say, how are these captured? Because there was no recent explosion. But once the explosion happens, the wreckage is there, and the light which we are receiving is billions of light years when the event has happened. So you're actually looking into the past. So this stars would have exploded long back, but then that light is still reaching us. So that's how scientists are able to recreate this using color code. Now this color code here used is the energy is used as a color code here. Okay, so what they have done is blue. So whatever images from X-rays given blue, and X-rays from this region are given as green, and the other from visible and infrared are given red. So here also these are some of the remnants of explosions which are there. So you can see the red, okay, then blue and green. So these are, you should take that are energies. Okay. Now, the Crab Nebula explosion, which had happened 1,000 years back, which was recorded by a Chinese astronomer in this form. Okay. Now, but scientists are able to recreate this, and let's see how it looks now. So this is the image the scientists have created of an explosion which has happened 1,000 years ago. So blue is neutral oxygen, green is ionized sulfur, and red is doubly ionized oxygen. Let's come to another image of Eta Carina. This Eta Carina is 100 times bigger than our sun. So it is, you put 100 suns together, and then this is what you get. Since it is so huge, it is very, very unstable, and it throws a lot of dust and gas. So it's very, very unstable. You can see from the image, it is throwing a lot of material out. Okay, so this would be the next supernova which we will be able to see. Okay, so this is an active one which is in space. Now the same image, if you look from X-rays, this is how it would look like. Okay, this is X-ray and this is infrared. Okay, and this is obviously the visible range. The other contribution of Hubble, before Hubble, there was no conclusive proof for black holes. So one of our professors used to say, oh, what do you do on black holes? You can't even see them, but we are able to map them. So astronomers decided to examine direct Hubble to examine the center of the galaxies. Okay, now the center of the galaxies, what Hubble has found is that using very, very simple physics is that the stars move at a relatively slow speed. Okay, so they discovered stars close to the center of the galaxies zoom around at a very high speed. Okay, so this should not be the case. As you see, they should go with a specific speed, but then what you see is that they're zooming around this with very, very high speeds. So the core, if you take the center, this is again, it's not a picture, this is an, you can assume it to be an artistic impression. Okay, so this area is zooming around very, very fast. If you don't assume there to be a black hole, the simple laws of physics are not able to explain it. So therefore, you assume that there is some supermassive black holes, and because of that, this material or this thing is going around this very, very fast. Okay, so all and the interesting part of is that all galaxies which we have found have supermassive black holes at the center of the galaxies. Okay, this is a mystery, but then this supermassive black holes we need to study and see how it has evolved into those galaxies. So they play a very, very important role. The other is Hubble's deep field view. Now, some astronomer decided to focus this telescope into a dark pitch of sky. Okay, means it's completely empty, and he wanted the Hubble Space Telescope to be pointed in that completely dark region. Now, one very, very important thing is that at no point of time, the Hubble Space Telescope can point towards the sun. If it points towards the sun, the whole equipment will go off. Okay, so it always has to point away from the sun. Now, some of the astronomers felt it was very silly, why you want to focus, because Hubble Space Telescope time is very, very important. But he said, no, I want to study this dark patch of sky. And then he pointed at that region for many days. And to the surprise, this was supposed to be an area like this, which was just dark, nothing. But then to his surprise, he found that so many of these galaxies and something. So astronomers became very, very excited, saying that you're looking at a dark patch in sky, and then you are able to discover, because these photons are coming very, very far off. That means you're actually looking very deep into the sky. Okay, so you can look here, 300 nanometers is assigned as ultraviolet, 606 is given red color, 650 as blue, 814 is the near infrared. Okay, so people got so excited, then they said, okay, let's look further down. So this is, you can say, is the Big Bang, where the whole drama started. Then this is the radiation zone, dark ages, the first star formations, and first galaxies to be formed. So Hubble deep field view is somewhere here. The telescope is here. So this is the normal galaxies which you see with the other telescope. And this is the age in billions of years. Okay, so Hubble's deep field view is still somewhere here. Okay, now some people wanted to look further, and that is called as the ultra deep field view. So you look still further down, that is back in time. So you're basically looking back in time. And if you're able to look here, then you will be able to see galaxy formations. And this is where Hubble is able to see till this point. Okay. So this is the deep field view, and we have extreme deep field views which are captured by ACS and wide field cameras. So Hubble spectroscopy confirms the farthest galaxy. So it helps us understand the age of the universe. So previous data was held by this. Now, if you look at this on the top, it is how do people decide what is the age of the universe? So they basically look at the redshift. I think all of you have done Doppler effect and you know what a redshift and a blue shift is. Okay, and this is the age. So the previous redshift which was observed by the stars was around 8.68, and the age of the universe which we could look back is 13 billion years. Now recently they have found this which has a redshift of 11.1. Okay, so the farthest galaxy ever seen in the universe, that is named as GNZ11. Okay, and that is around you can say 13.4 billion years. Okay, if you can go back further, okay, the James Webb telescope intends to look somewhere further, and James Webb's telescope will be in the infrared region. So what we want to do is go back and see how the Big Bang. So coming to a very, very important thing, I think this should, many people have a misconception about this. Okay. So what Hubble has found about the beginning of the universe, Hubble has measured the age and size of the universe before, better than before. Okay, so you have new data. So the question is, was Big Bang an explosion? Okay, normally everybody assumes that there was some explosion which was of a conventional type, and then the Big Bang started. That's a wrong way of looking at Big Bang theory. It's not an explosion, it is an expansion. What do I mean by an expansion? At Big Bang, the space and time was created. So space itself is being created. So if you, to give a very simple example, if you're taking, like say, two stars, the stars are fixed, but the space between those stars itself is increasing. So the space is expanding, and it is, you need to understand that space and time itself was created, and you not take it as an explosion. Why not an explosion? If you say an explosion, then there has to be a point where the explosion happened. And there is no point of explosion in Big Bang. So if there was a Big Bang, if you assume, then the next question would be, please tell us where the explosion actually happened. Okay, and then there is no reference point for that. So we don't take the Big Bang as an explosion. So next time you say it is an expansion or it is a creation of space and time itself, you would say that, what about the Earth and Moon, let's say? Yeah, the space between Earth and Moon also is increasing. It is increasing very, very slow. But the space, they are fixed, but the space itself among them is increasing. So how galaxies rotate did not make much sense, as the arms of the spiral galaxy tend to move faster than the laws of would allow. Now I'm coming to galaxies here. I'm basically going to dark matter and how this. So what I do is this edges which when I calculate, I do the calculation for this at the rate at which they are going around. The laws of physics don't allow it, because if I add up the whole mass, okay, so the whole mass of this galaxy will try to hold it together with gravity, and the centrifugal force will try to throw it out, right? So the whole mass in this galaxy is not sufficient to hold it there at that speed. Okay, so if it is not able to hold it there, then how do I explain this? Okay, so we try to look at an answer for this is that, yeah, so that is what we call as dark matter. Okay, so galaxies are surrounded by a hail of unknown form of matter. Okay, this matter acts like a glue and holds the universe together. Yes, Hubble has been able to map this dark matter. So even though we don't know much of its properties, but the map is there. We call it dark matter. How has Hubble been able to map it? If you look at relativity or general relativity, what it says is that if you have huge mass here, okay, and the space and time around this will get curved. So let's say we are here, or the Hubble is here, and this star is, or galaxy is exactly behind it. So what do you expect to see? Nothing. You will be not able to see this because this is exactly behind it. But the point is that you are able to see it. So this is called as gravitational lensing. Just like you put ordinary lenses in optics to bend light, to focus it, here that job is done by gravity. Okay, because the space-time is itself curved and the light is going along a straight path, which is the curved path itself, and therefore you can see this galaxy which is exactly behind this. Okay, so what is the universe made up of? So the universe is made up of 4% of matter, which we actually know. So 22% of it is dark energy or dark matter. Okay, so 22% is dark matter, which I just told you it has been mapped. And the 74% remaining of it is, we have no clue of what it is still. Okay, so what is the 74% of the universe made up of? The answer to this again comes from Hubble, or Hubble's data, you can say. Okay, so after the Big Bang, okay, after the expansion, we assume that as matter is being created from energy and gravity is pulling it this thing together, so the gravity should slow it down. So over a period of time, the expansion of the universe should slow down. That is what we expect or believe, that the universe is slowing down. Okay, there was a team of 2 experts who looked at the Hubble's data, and the data showed them something different. What they found is that the universe is not slowing down, but it is getting accelerated. It is expanding at an accelerated rate. So Hubble's finding does not fit the expected model for expansion of the universe, but okay, so it's not expansion of the universe, but it is showing us that it is accelerating. So it is not just expansion, but there is an acceleration. That is what Hubble's data is showing us. The galaxies with supernova are not just moving away. Okay, they are moving at an accelerated rate. Okay, Hubble's results convince astronomers to think of the universe in an entirely new way. The value of the universe expansion rate, you may say, what is the accuracy of your calculation? You're saying it is accelerating. So how much to believe that data? Okay, so we have to look at that. It has been calculated with a precision of 3%. So there's no problem with the data part of it. So normally in a lab experiment also you accept the result up to 5%. But this is much lower than that, which is 3%. It can be refined further. So the new value implies that dark energy really is a steady push. So as you know that we have four fundamental forces in nature. People were playing with this idea of a fifth force, which is like pushing the universe or apart. Okay, so steady push on the universe as Einstein imagined with this gravitational constant. I think I end my talk with this. Any questions? I would like to maybe.
Yeah, thank you, Shaker Garu. Thank you for that wonderful presentation. Yeah, sir has got a question.
Sir, I am Malaya from Govt Degree College, Pithapuram.